All right, looks like a few of us are trickling in right now. Um, how's everybody doing today? All right, here's the document for notes today. Oh shoot. I ask you that to make a copy of that. Most of you are not going to have, none of you should have editing rights to it, but if you'll make a copy of it, then you can edit it in your own way. And then again, here is the presentation for today as well, so that you have that as well if you want it. All right. So with that said, let's go ahead and get started today with our presentation. All right. So today we're going to start talking a little bit about the wonderful world of matter. And in particular, right now, we're just going to talk about how, well, the different phases of matter. We've already talked about um, matter as far as, by definition, matter is anything that takes up space and has mass. Well, now we're also going to talk about a little bit about the different phases of matter in this lesson. So our lesson objectives are today to be able to define matter, learn the fundamental definition of matter and its properties, explore the floor, four states of matter: solid, liquid, gas, and plasma today, and understand the phase changes that occur and why those phase changes occur and why there's actually different states of matter as well. It's all driven by theory called kinetic molecular model theory, which just really means that all matter is made up of um, atoms, and anytime we add or subtract energy, we affect the movement of those atoms. So the more energy, the more the atoms vibrate; the less energy, the less the atoms vibrate. And that's what changes the states of matter. So we can have water in a solid state, a liquid state, and a gaseous state. All right. So let's start with the one with the lowest amount of energy. The lowest amount of energy is the solid state. And the solid state is literally that. It cannot change shape, it cannot change volume. The molecules are not free to move wherever they want to move to, or really move much at all. They do vibrate, and as a solid heats up, the solid will vibrate more and more. Now, there are two types of solids: there's the crystalline solid and the amorphous solid. And you're going to say to yourself, what's the difference? It's a solid. Well, a crystalline solid is characterized by highly ordered three-dimensional structures. What we mean by that is there's a three-dimensional pattern to how the atoms line up, and by having that arrangement, they can take on very specific shapes. For example, if you look at mica, which is a very specific type of rock mineral, it layers up. So you can peel it like you were pulling two pieces of paper away from each other, because the three-dimensional structure is lined up so that it holds two dimensions very well, but the third dimension is in nice even planes, and it allows them to peel specifically apart. Another crystalline structure that everybody is aware of is diamonds. Diamonds, you really can't cut diamonds. You can break diamonds along what are called cleavage planes, and those cleavage planes exist because of having a very specific crystalline structure. Salt, same way. If you ever look at salt under a microscope, it will always look like a square because the sodium chlorides line up in a very specific pattern that forms a square. Now, amorphous solids, on the other hand, amorphous means there's not an arrangement. So the molecules are there, they're bonded to each other, but they don't take on a specific pattern. They're very random, and that allows them to form very different shapes. They don't have very specific shapes when you get to the anatomic level. Glass and plastics, rubbers are all very good examples of amorphous solids. Most people don't realize that glass does flow. It is very viscous. It flows very, very slowly. It is a solid because it's moving so slowly. But over time, if you go look at one of those old farmhouses out in the country that have been there since the early 1900s and no one's living in them anymore, if you start looking at the pane of glass, it's always slightly thicker at the bottom than it is at the top. And that's because the glass molecules, basically the silicone that makes up the glass, the silicone atoms, can adjust shape over time. All right. Our next phase is a liquid, and liquids have the ability to flow. And the reason they have the ability to flow is because they have the ability to have their molecules move around. They are not bonded together with as many bonds as a solid is, because liquids have more energy stored in them, and because they are vibrating a little bit faster, there's fewer bonds that can form, and that creates more of a chain effect with the matter, and that allows it to be able to flow. So while it's still incompressible because it has a very uniform or very I want to say solid, but solid is not, it is not a solid, but it does not have the ability to compress. Incompressibility means it's going to maintain its volume. That's what I'm looking for. It's going to maintain its volume so that the volume will not change. The shape will change, but not the volume. And because of that inability to change volume, liquids will form what a surface tension. And water is a great example of having surface tension. How many of you have ever done a dive off of a diving board or the side of a swimming pool and hit and had it hurt because it was a belly buster? Yeah, that belly buster, or the reason it hurts, is because of what we know as surface tension. Water is made up, we all know water is H2O, and water has two hydrogens and an oxygen atom that kind of form a V shape with the two hydrogens here and the oxygen up here. Well, the hydrogens are slightly positive and the oxygen has a slightly negative charge. What do we know about charges? Opposite charges attract, right? Well, those opposite charges, the oxygen from one water molecule will also attract the hydrogens from another molecule. So there's a slight attraction there. So they kind of form a sheet on the top of the water, and you have to break those bonds to be able to get down into the water. Yes, water, I see that Oscar says that always thought water saves you from falling. Yes and no. Depends on the height and actually how you hit the water. There's a reason why divers are always trying to hit with their toes pointed or their hands up above their head, and that is so that they can break the surface tension with a small amount versus flat. The flatter you hit, the more bonds you have to break of the surface tension, which requires more energy. There is a reason why people die when they fall off of very high bridges. It isn't from hitting the bottom of the water. For example, unfortunately, people have committed suicide off the Golden Gate Bridge, and they've now kind of tried to put nets and things underneath so that they can catch them before they fall too far. Even if you survive, you break bones and things like that. And that is because you are traveling and have so much kinetic energy that when you hit the water, it has a surface tension and it doesn't move. The molecules don't separate fast enough to relieve that amount of energy. And it's almost like hitting on concrete. So you need to be aware that, yes, low amounts, water does absorb low amounts of energy relatively well. And when you fall, it can stop you, but that's also why it hurts when you do a belly buster or something like that. You don't want to land flat. Now, the higher up you are, the faster you are hitting the water as you're falling, because you're increasing speed as you fall to a certain point. And the higher the energy, the less likely it is to be able to spread the water fast enough, and the more damage it can do as well. And a lot of that has to do with this surface tension and then what we call viscosity. And viscosity is a measure of how much a liquid tries to avoid flowing. Most people, the only time they hear the word viscosity is when they hear engine oil commercial, and it talks about viscosity there. Viscosity is just a measure of how material does not want to flow. The more viscous it is, the more complex the arrangement, the less likely or the slower it flows. The example here is honey. Honey flows slower than water. We all have seen that. Well, honey is very viscous. Water is not. So when they talk about viscosity of oil, the higher the viscosity of oil, the less likely it is to flow. So some engines that run pretty hot have a higher viscosity oil because they need to be able to, that viscosity needs to be able to add energy to it. And as you add energy, the more liquid a liquid becomes, I guess, the more viscous it becomes. So high viscosity oils are for high heat engines, whereas your lower viscosities are for ones that dissipate heat pretty well. All right, our next phase is a gas, and gases are compressible. And they have a lot more energy in their molecules to the point there's not very many bonds at all. And gases have enough energy that now they can fill the container that they're in. So they don't have a set volume and they don't have a set shape because there's so much energy in the molecules they're balancing around now. They have enough energy to overcome gravity and fill whatever container they're in. And because the gases can move, the particles can move away from each other, that allows them to be compressible. So you can compress gas, and that's what you see when you look at gas. When I'm talking gas tanks, those air tanks that people use to breathe, or if you live in the country like I do, and you might have a propane tank where the gas, your propane is stored and compressed into basically a liquid to that point. Gas also has the ability to diffuse, which is what I was just talking about, the ability to spread out and fill containers and move apart. And then it also has the ability to effuse. And when we talk about effuse, we're talking about the ability to move through very small openings. So effusion is the ability to move through very small openings that maybe a liquid is too big to pass through and a solid definitely won't. So there's that. Looking up here, Oscar, you've asked, what about CNG buses like the new Flyers? I'm not sure what you're talking about there. So if you give me a little more information, I might be able to tell you something about them, but I'm not real sure what you're talking about. So that's above my pay grade at this point. All right, our fourth energy state or phase of matter is plasma. And plasma is a superheated gas. Remember, when we go from solid, you add a bunch of energy, becomes a liquid, add more energy, it becomes a gas. And then finally, at a super high energy, a gas can become that can become a plasma. Yeah, compressed natural gas. You see those in containers as well. Yeah, they are definitely compressed. The little propane tanks you see on your propane grills and things like that work that. And your CNG. I've never heard it called CNG. Thank you for lessening me today, Oscar. I learned something, and hey, that's good for me. So, compressed gases are just gases that have been had the particles pushed together, and it creates a tremendous amount of pressure. And we'll talk a little bit more about what pressure does to things in a second. Plasma, the fourth state is here. It says an ionized gas. Resulting in free ions and electrons. This ionization leads to the unique properties of plasma. Plasma becomes very electroconductive. It can conduct electricity very well. That's why we see lightning. That's why I have the picture of the lightning bolt over here. It has the ability to be responsive to electromagnetic fields. Anytime you start dealing with electricity, you are dealing with electricity and you are dealing with electromagnetic fields, and all electromagnetic fields are electricity can create a magnetic field, and moving magnetic fields can create electricity. That's how we use generators. By spinning generators, all we're doing is spinning magnets around copper wires, or copper wires are being spun around magnets, and that produces an electric current that runs through the copper wire. So that's how we use generators. Now, plasma is a glowing material. You've seen lightning, some different types of light bulbs are like fluorescent light bulbs are a plasma. There's a tremendous amount of electrical energy running through a gas, and that the gas molecules are now vibrating as fast as they can vibrate, and they can't vibrate any faster, but they're having more energy added to them. That energy has to have a place to go, and that energy gets released from the gas in the form of light. So when we think about plasmas, we're thinking about things that are glowing and are gases that are basically releasing light. Neon lights that you see at the tattoo parlors, your barber shops, some of those types of things, the ones that say open on different stores and stuff like that, those are plasmas. What is happening there is there's a tremendous amount of energy being put into the gas, the neon gas in the tubes, and that those gases vibrate to the point that they can't vibrate any faster. And as that more energy is added to them, they have to get rid of it somehow. And they do that in the form of light. So plasmas are kind of a cool situation, and they are the highest energy phase of matter. Okay. So now we've kind of talked a little bit about the different phases. Let's talk about phase transitions. If we have solid water, which is ice, and it goes to liquid, what do we call that? You all know the answer. Ice
Melt,
does on a hot summer day.
melting.
It melts, right? So that is the phase change from solid to liquid, is what we call that melting. To go from liquid to solid, we call that what? Water does what as well? If you take the energy out of it, it's going to freeze, right? So melting and freezing happen at basically the same temperature for different materials. Like water, if we were to do it in the Celsius scale, water freezes at 0 degrees. It also melts at 0 degrees. And if you look at this chart that I have over here, you'll see, notice at the bottom it says heat supplied. As we add heat, or we could change this word to energy, to water, when it's ice, the temperature will go up until it hits the melting point. Once water hits its melting point, energy that is being used from along this line here, notice the temperature isn't changing because the line is flat, right? That is where melting is occurring. So as we add energy, the energy is no longer changing the temperature. It is being used to change solid ice to liquid water. And conversely, if we take that energy away, liquid water will become ice. And then we hit another spot where now the temperature starts going up again because the energy that we're putting or applying is no longer melting the ice. The ice is all melted into liquid. Then the temperature can rise again and heat the liquid until it becomes a point where it hits gas. And here it says condensation and melting point. I chose a bad picture here because this should be what? Vaporization and condensation. Because when you boil water, what happens to the water? It vaporizes and goes from a liquid to a gas. And that's what this point represents. This flat line is, we're now adding energy to liquid water and it's going to become gas. And then once it gets to the point that all the water is gas, the gas will heat up again and its temperature will begin to rise in the form of steam. Conversely, we can have cool gas down and it will condensate, aka condensation, and that's changing a gas back into a liquid. I don't know how many of you know how a moonshine still works. I've always been enamored with that goofy show, Moonshiners. But basically, what they're doing there is they are taking alcohol and water that is in the what they call the mash, and they heat it up, and it becomes a gas, and take it to a gaseous state. Well, what they're doing is they're actually using the fact that alcohol boils at a different temperature than water does. Alcohol boils at a lower temperature than water. So they can separate the alcohol from the water by heating the mixture up, and the alcohol will start boiling before the water does. And the temperature of the mash of the mixture will not go up until all the alcohol is boiled off. Once all the alcohol is boiled up off, the temperature will start rising again to the point that the water will start boiling. But with alcohol boiling, I want to say at about 82 degrees Celsius, which is about 18 degrees lower than water, the alcohol will all boil off at 82 degrees, and the temperature of the mixture will not go above 82 until all the alcohol is gone, and then the temperature of the water can rise again. And at that point, that's when they stop trying to separate them because they know they've already separated it. And a lot of this occurs not only with alcohol, that's how they separate using oil. That's how they separate gas, turpentine, things like that, different oily materials apart from each other. So that's just the phase changes. And we just have to recognize that when we're having a phase change, the temperature doesn't change, but we are either adding or subtracting energy. All right, here's two special cases of phase change: sublimation and deposition. Sublimation is where a frozen solid skips going to liquid and goes directly to gas. How many of you know what dry ice is? Anybody out there know what dry ice? It's basically solid carbon dioxide ice with smoke. Pretty close. Dry ice, the dry ice itself, you do not want to touch with your bare hands because it is cold enough that it will freeze the water in your hands and can cause some skin damage. Dry ice is solid carbon dioxide. And yes, when it heats up and gains energy, it does not go to liquid. It goes directly to gas, and that's what you see as the smoke. You want to keep something cold in a ice chest. Dry ice is the way to go. I've actually been able to freeze those popsicles by putting dry ice in a cooler with those little thin plastic tubed ices that you can buy. Put them in there, leave them for a while. The dry ice is cold enough that it'll actually freeze the water in those in a cooler without having to have a refrigerator or something like that. The opposite of that is what we call deposition. And deposition is where a gas goes directly to a solid. And we see that with some regularity when it snows. Snowflakes are a form of deposition. The water vapor in the air freezes directly into a solid and falls as a snowflake. That's why we get those snowflake crystalline structures. All right, last thing for the day: phase diagrams and visualizing phase transitions. We've talked a little bit about how energy changes cause changes in phases. Well, there's one other thing that affects phase change as well, and that's what we call pressure. Most people don't realize, but if you add pressure to a material, the more likely it is to become a solid. There's one exception. Anyone know what that one is? Water. Liquid water. Water expands when it freezes. I'm sure you've all seen that, where you take a pop bottle, put it in the freezer, and it expands when it freezes. Well, because water expands, if you put pressure on ice, you could try this. If you have a big chunk of ice, take some small weights, tie them to a string, put the string over the ice, and over time you'll see that string cut through the ice. And that is because the pressure is pushing the molecules closer together. Well, water's molecules can get closer together in liquid form than they can in solid form. And it's the only substance in the world that does that. Everything else, the tighter you try to press it together, the more likely it is to become a solid. So if we put, I don't know how many of you have ever seen one of those Instapots or a pressure cooker, but that's what they're doing. Is you can get water to a higher temperature by putting it under pressure. It will stay in liquid form longer before it comes to a gas, and the temperature at which the water boils under pressure is higher than it is when it's not under pressure. And that's what this diagram shows. So if we look at this, I don't know that this is necessarily a water phase diagram, but here we see this point. This is where solids are going directly to gases and gases are going directly to solids. So when we create dry ice, they take carbon dioxide in its gaseous form, cool it down, and then put it under pressure in like a propane tank and squeeze it together, and it will go directly to a solid. When you relieve the pressure and it starts to heat up, it'll go back to gas. Here we see that the temperature changes between melting and freezing between the solid and liquid as the pressure goes up. Same with the liquid and gas. Now there's this point here that's called the triple point, and that's a temperature and pressure at which a material can exist both in all three states. It could be a solid, it could be a liquid, and it could be a gas at that temperature and pressure. And the molecules are constantly changing back and forth between the three states. And then finally, the critical point. The critical point represents the temperature and pressure beyond where a distinct liquid and gas phase exist. And then you're starting to get into a supercritical fluid, and you're getting close to becoming a plasma. All right. Are there any questions over any of this? No one has any questions today, huh? Well, I want you to think about it. Know what the four, think to yourself, what are the four phases of matter? Can you tell me the difference between sublimation and melting? Can you tell me how they're the same? Those are things you need to know from this lecture today. All right. All right. If there are no questions, we will call this a session, and I will see you all again next week. Have a wonderful day. Okay.